Hello, welcome to this session for the J Champions Conference. This talk, Serverless Java Hacks. Andro, take it away.
Yeah, thank you, Barry. Welcome to my talk. I'm Ondro Mihali. I'm founder and director of Omnifish. And today I'm going to talk about how to approach programming serverless functions. Mostly, it's about functions, but also in relation with other services in serverless deployments, and how writing or what you should care about when you write especially Java functions, but some of that applies to also other languages, but you're here for Java. I believe so. I think I'm on a good spot. uh, and how writing these serverless functions is different than writing normal applications, and why. So I'd like to make you understand how you should think differently when you write decent code in Java, when you want to deploy it on the functions. So first about what is serverless computing, and sometimes it's called serverless, sometimes it's functions, serverless functions. Uh, there are small differences here and there, but I will always use them to mean serverless functions, which is the small piece of code usually, or maybe a bit bigger, but not like a full-fledged application that you can think of. Like when you deploy it on a server, it's usually a smaller application that does one job and does it well, like something like a microservice. Um, and it has its own advantages and also sometimes disadvantages, but mostly the advantage is that you can just write the code and deploy it almost without maintaining infrastructure. You always have to do some tweaks or some configuration details to configure the domain name where your code listens to or accepts HTTP requests. It can also accept some other events and inputs. So you need to configure it how it deploys to the environment. But besides that, you don't need to prepare a server. You don't need to set up some tuning, monitoring. It's already there, usually by a cloud provider, and it's also prepared to scale. So you can deploy once your application. You can have scalability to zero, which means that you don't pay for this application to be running. Uh, Most cloud environments, you don't pay even that the application is deployed. Maybe you pay for some space, which is very cheap. But if the application actually doesn't consume CPU, it's very cheap, close to zero. You can forget about the price of the cost in cloud, or of price of the storage in cloud, especially for these small artifacts, which are functions. And then when you need the application to actually handle requests, you can scale, you can have multiple requests running, which means multiple applications will be started. For each request, in general, you have one instance, one application from your code running. And usually in the cloud, it's possible, the cloud providers make it possible to run multiple, lot of functions at once, so you can process many requests in parallel, close to infinity. It's not real infinity, there's always a limit, but in practice you rarely can get even close to the limit. It can go to thousands of parallel executions of a single function. And then, of course, if you have multiple functions running, each one can scale up to thousands of invocations in parallel. Um, and you don't need to set this up front. It's just you deploy your code, and when nothing is coming to your application, you don't pay anything. There is only zero instances. And when there is incoming request, for each request, there is one new instance triggered by the provider, and you don't need to really care about it much. What you pay for is actually when your application is running and consumes CPU time. So when it's not running, it's zero cost. When you scale up to thousands of invocations and each invocation takes 10 seconds to finish, then you can imagine you have to multiply this. So when you need the computation power, you have to pay for it. But if you don't need it, you don't need to pay. Um, the actual AWS Lambda invocation has a certain life cycle. I will be talking about AWS Lambda, which is one of the examples of serverless functions. It's a way how AWS Cloud implements this serverless functions as AWS Lambda service. Other cloud providers have their own implementations which work more very similar to AWS Lambda. There are some differences. Then we can have also hosted and on-premise implementations where you have to manage your cluster yourself, but then you can deploy serverless functions onto this cluster, and then the cluster or Kubernetes or something like that manages your functions. So in case of AWS Lambda, and also in general, most of the times, there's initialization phase of the function. So let's imagine that in the beginning we have nothing running. You deploy the code, there are no requests coming to our application, so there are no instances of our application running. We pay nothing. Then there is one request which comes and it wakes up our application. Then it has to go through the initialization phase, through the init phase here on the left, because it's not running at all. It has to be initialized. It means that some extensions into AWS services are initialized. The runtime to power our code is initialized, including the virtual machine and also like something like a Docker container. You can imagine it if you already know what is a Docker container. And then your function itself has to be prepared. So in this phase, also some Java code is running. Basically, it creates the object that you write without calling the method that handles the request. So it prepares everything just to be able to handle the request, including JVM process invocation. So it starts the JVM process and pauses it before it handles requests. This is also called a cold start because this happens only when your application instance, when your function instance is not running. It takes some time. It's like when you need to start an application from scratch. When the application is already running, then it's just a matter of calling a Java method to process the request. So the second phase, invoke, happens for every request, every event that comes to your application. And if the application, if the function is already running, it's just a method call. So this is very quick, and it repeats until your application is active, is ready to process requests. But after some time, if the function is not used, is usually minutes, 5, 10, 15 minutes, the provider may decide to shut it down to save resources. So we don't pay for this, but the provider usually pays for these resources while our function is running. So it shuts it down after some time. So that's also the provider doesn't have to pay for the CPU reserved for this function. So it goes to the shutdown phase, where again the extensions are unloaded, the runtime is discarded, and it basically goes back to shutdown state, like the zero state we had before. And again, when there is an incoming request, it has to initialize. It has to go through this cold start again, and then it's ready to process multiple subsequent requests. So these initialization and shutdown are basically what needs to be done because in order to make it possible that the function goes to zero or scales to zero, so that when we don't have any work for it, we don't have to pay for it, there are no resources consumed. There is an optimization that it doesn't happen for every request. It only happens when after some time the function is not used. But if there are requests or events coming to this function, it stays in this invoke state and processes request without the cold start. This is usually in milliseconds. It's very fast because it's just like when you execute a method from your code. So in this model, when we pay for the time that the function uses the CPU and we don't pay when it's not triggered, there are some things we need to avoid what we were used to before, especially some optimizations in our traditional applications, because now we need to optimize in a very different way. Before, or with traditional deployments to servers like Spring Boot applications, deployments to Kubernetes microservices, or even bigger applications, we usually optimize in the beginning, try to prepare for future loads, and when incoming requests are coming, the application is already optimized. The reasoning is that it's very rare to restart the application. So it's good to have everything optimized before, and then it's ready to serve requests all the time. And there is very little cost when there is very high cost actually when we stop the application and start it, but it happens very rarely. Which is the other way with functions. With functions, it happens very often that functions are restarted, they are shut down, they are initialized, and the cost should be small. And that's what we try to achieve. Another thing is that because these functions are often restarted, we cannot keep state in the JVM itself, in the program itself, because our function is no longer one process that keeps running. It's multiple processes, and we don't know how many processes it will be, which are started and then shut down, started, shut down, started, shut down. It may be running all the time if there are incoming events all the time. That makes it busy. But then maybe there are more requests coming and we want to process them in parallel, and multiple instances of our functions are executed. So the function is started again and again. And then maybe we need fewer instances of our function. So uh, I'm sorry, my child just entered to the room. So I'll continue. So when the function invocation instances are scaled up or down, we have new instances and existing instances are shut down. So we cannot really keep state in those functions, because when they are started, there's no state from the previous invocations. When they are stopped, we lose the state. So, and this state is not even shared because there are maybe multiple different processes. They have nothing in common, just the code. We have to approach to state in a different way. Then there is synchronous I/O operations. Why I mention it is also in traditional applications, there is a cost to synchronous operations because your thread is waiting for database or for a file system operation to finish. And then it takes longer to respond, and you can have only so many threads unless you use virtual threads with Java. And that's why basically reactive frameworks happened to save the resources and make things asynchronous to optimize. For serverless functions, there is a different reason to avoid synchronous operations. Basically, you can have synchronous operations if they don't take very long, because with asynchronous operations, you won't speed up processing. it will always take time until you have a response from some database. You can't cheat or can optimize it with some asynchronous operation and then wait for database to come to you. You can, but only if you have something else to do. In serverless functions, you very rarely have something else to do because you focus on one task. You wait for data from the database or from some external service, and then you continue. But it's good if you can optimize this so that you can invoke several functions changed by events, because the problem is when you wait for an IO operation, even though you don't do anything, don't consume actual or don't you make use of the CPU, uh, it still computes to your cost. Even if you don't utilize the CPU, it's zero usage. The cloud provider allocated the CPU to your function, and you can use it. And even if you don't use it, you have to pay for the time that it's allocated to you. So if you trigger a function, it takes 10 seconds to connect to the database and read data to it, and your function does nothing, you still pay for that 10 seconds. And there are other things that I will mention earlier. One is resource pooling, which is also an optimization for traditional server deployments. But with Lambda, you usually have only one resource of a kind. You have one thread, one database connection, because you're only serving one request at a time. So sometimes this resource pooling makes sense if you have special case when you need to process multiple things or connect to multiple to the database and ones with multiple parallel threads. But usually you use only one thread, one request, and then you don't need resource pooling. Similar with prematured concurrency. If you try to create too many parallel invocations, then you cannot utilize these. If you use multiple threads, you cannot often utilize it for just one single request. So if you have some framework that prematurely creates multiple threads, and you're going to be using only one thread, there's no reason to use this. And the last thing is when you understand how package size and the amount of code that you add to your libraries, to your applications, which means if you package a lot of libraries into your application, then it has impact on how long it takes to start your application. In normal microservices or server-based applications, you don't start the service very often, so it's not so much of an issue. With functions, you want to reduce cold starts as much as possible, and you don't want to have a lot of rubbish in your application that you don't need. So what to do instead of this? How to address state? If we can't state it as a store state in our functions, there's nothing like. Normally, you wouldn't do that with persistent data because you store it into database. Even if you have normal applications, they can sometimes be restarted and then you would lose the state. But you could store some data for sessions, for example. And in serverless functions, this is also not possible because even you cannot even connect multiple requests with a session. They are completely isolated. You have to somehow connect them by some other service that is not so serverless. It has to remember something. Either you store everything into database, even session data, or you have to use some caching mechanism outside of your functions like Redis or some other distributed memory cache. But for some things that you can recreate is still worth to cache. And caching actually in serverless function is quite straightforward, not something you would use in other and other scenarios. But in the serverless function, I would recommend to use very simple approach to store data in a global variable. And the reason is that you have only one thread actually accessing it, so you don't even need to uh, check or implement some thread safe manners to store the variable. You can use any map or anything, any structure to store the data, because you know that only one thread will be accessing it at a time, at least in AWS Lambda. If you have other cloud providers that have some possibility to run multiple requests on the same function, then you may need to do some synchronization or create two different structures for two different invocations. But in general, there's only one thread running on a function, and when the function is reused, it's reused for subsequent events. So it's reused for things that go in sequence and never in parallel. You can store something in cache from the previous invocation, and the second invocation will already have it in this global variable, but there will be no conflicts, because these requests will be processed one after each other. So this is an example of just how you can imagine. The only thing that might be new to you is the actual method definition for AWS Lambda, where we have this handler request method we create in our code, and AWS Lambda understands that this is a method that it can call when there is a request. And if we connect our serverless function to API gateway in AWS cloud, then the API gateway will actually accept the HTTP connection from the outside world, turn it into a JSON data that represents this request. Sorry. And the AWS Lambda service will turn this JSON into a Java object for you, which is this API gateway proxy request event. And we can also accept a context which provides some additional data about or information about the AWS environment. And then what we need to do is to produce a response event, which is again more or less JSON that API gateway understands. But we can also, if we want to just trigger some other event, we can from our code trigger a message from SNS or other notification services in AWS Lambda, and just respond with a very small response, HTTP OK or something like that, so that the API gateway has something to send back, but the actual computation will be done asynchronously and triggered by events, and finally it triggers an event. And the rest is just using a hash map or anything you know as a cache. So it's good to cache data, but it's not good to rely on the data that you store. It should be some hash map with a mechanism to retrieve the data if it's not there. So you see here, I use the map as a cache, and if I'm using Jakarta persistence API. So if I stored a person entity before and it's still in the cache, I can use it. But if it's not there, I need to have this logic to retrieve it from database. I cannot just rely that previous invocation stored it in the memory, because meanwhile my application, my serverless instance could go down, or a new one could be created, so I would lose the data. Another thing is, which I mentioned, is that when you execute a function and it executes, or it waits for some IO operation, or even executes another function, and that one executes another function, you can have chain of invocations of other services that are actually implemented as AWS Lambda functions. Then the first function has to wait until all the functions return, and you pay not only for the time that your actual code executes, but also for all the functions that wait for other functions. You can see it like here. When function 1 invokes function 2, and that one invokes function 3, the function 2 needs to wait for function 3. Then it can continue with the result, do some processing, return result to function 1. And function 1 keeps running all the time. So we pay for all the time for function 1 plus some time for function 2 and also some time for function 3. While in ideal world, you would pay only when the code or when you use the CPU. So after you call function 2, you shouldn't pay for function 1 execution. And then also for after executing function 3, you shouldn't pay for function 2 execution. And the way how to achieve this is to split your logic into asynchronous calls, so that when you invoke function 2 from function 1, you complete function 1. If it's coming from if function 1 was started by an HTTP request, it's hard, because in that case, if you want to return the actual result in the HTTP response, you have to wait at some way or the other. You can optimize maybe function 2 and function 3 calls, but you have to wait until you have the result. But if in that case, if you can, I recommend to separate these function calls into two steps. One is to invoke the HTTP request and return a quick response, and then the client can either poll for a result or use a WebSocket or something to communicate to retrieve the actual result at the end. If you don't have to do that and you respond just to events, it's easier. Then function 3 at the end can just invoke an event, and then some service or some other function or whatever responds to a result. Or maybe at the end you don't need to trigger an event. It's enough to store data in the database and you're done. This also applies if you store data in the database, and if you use serverless databases or cloud or databases that have some support for events, you can also use this mechanism to implement what I'm telling you about. Function 2 can store data into database and finish. And then function 3 would be notified by the database, not by function 2 directly, but after this mechanism, after the data is stored in the database, then you can set up an event that the database triggers an event, and DynamoDB can trigger an event on specific cases when you update a special type of data. There are it's not an SQL database, so it's not so easy to say like if a specific table is updated. But if a specific resource is updated in DynamoDB or an S3 bucket is updated, then you can respond to an event, and function 3 would start after this data is updated. And then again, you pay only for the time really when you really use the CPU, and you don't have to pay for anything running while you do the I/O operation. That leads to another thing. When we start talking about or thinking about databases, normally to optimize our applications, we would use connection pools to create some amount of connections that are active and are ready when we need them, because creating a connection is slow. And if we want to have cold starts small and start our application fast in serverless, we should avoid doing this, because then multiple connections would be created, but we actually, as I told you, we normally process only one request at a time. So we only need one connection to the database. The same is with thread pools. We don't need to create or prepare more threads in advance, or even have the mechanism of keeping multiple threads running, because we will use only one thread. And there's no reason to pre-create and hold multiple threads. So in this case, it's simpler than with servers. Basically, the cloud provider does that for us. It pulls our serverless functions. If they are not needed, it will shut them down. If they are needed, it will scale up to as many as instances as are needed. Uh, what we should do instead is cache resources. So we connect this to the caching that I mentioned to you. When you need a connection to a database, you create it, and then you store it into some global variable, into some mesh, if some map. If you have multiple connections, if you only have one database, you can have just one global variable, store it there, and then for the next invocation, it should be already active, because the previous invocation will be just at most 5 minutes or 10 minutes before our invocation. Otherwise, our Lambda would be shut down. So if our function is executed again, and it already has this cached database, uh, it had to be used previously in a small period of time. So we can use this caching, and our connection will be probably active and will not disappear, will be not be interrupted, especially in cloud. These things are pretty reliable. If you have a connection to a database that is running outside the cloud, that might be not so reliable, but then you can implement some validation mechanism to validate if the connection is still active and use it. You have the same thing in connection pools, to be honest. If you deploy to servers without serverless functions, you just don't need to create multiple connections. You just create one connection when you need it. I recommend to cache it. And if you want to be sure that the connection is still active when the Lambda is executed again, you just implement the same validation as you are used to. For example, just issue some simple select to a database, or just some ping method to a database to make sure that the connection still is active and you can send queries to the database. What we can also do, if we really want to optimize this, and this really makes sense in serverless environments, to optimize to very short execution time and very short cold starts. These are two different things. One, cold starts only applies once in a while, but usually it takes some time to start the application. Some applications may start even seconds, 5 to 10 seconds. Sometimes it's just 1 second. It depends on how big your application is and what framework you use to build your application. But then even if the application is started, it matters how long it takes to actually process one single request. Because for one single reason, you pay for the time. And if you pay less, it's good for you, and you pay less if the function takes shorter to execute. And if we connect to the database when we need it, we still need to wait for the connection to happen. If we cache it, we can skip it. But if the connection to the database is not cached, then we have to create it. Or if it's stale and we have to recreate it, we need to wait at this point until we can work with the database. And this may take some time, maybe negligible, maybe not so negligible. Usually it's some money you have to pay, either small or bigger amounts. And the solution is to think about pre-creating everything before you even need it. And here it's good to use threads, especially daemon threads, which disappear if the application is shut down. But even if you don't create daemon threads, AWS Lambda basically would suspend your application after your main method is finished. So if your main method doesn't need your connection, it will stop the whole virtual machine after the method is down. And then it doesn't matter if the connection was created meanwhile, or it's in the middle of creating the connection, because that's when your main method finishes, everything is stopped or paused, let's say. But from the matter of what the computation can, or what the application can do, it's basically stopped and cannot do any more after this point. So you don't pay for the additional CPU time after your main method returns. But you also don't pay for any other threads running at the same time. So you can have multiple threads running and you only pay for one of them, basically, because you pay for the time, not the actual CPU usage. And meanwhile, you do some preparation, for example, parse the event to a Java object, or do some processing to prepare the data that you want to uh, save to the database or something like that. Meanwhile, you can connect to the database or verify that your cached connection is active and responding, and you can save time after your computation is done and before you need the database. So this is a way how you can think about optimizing actually the time you spend in your functions. And in functions, it matters. In other environments, it doesn't matter so much because you have connection pooling and everything is basically prepared. There are other means of optimization. But in serverless world, you basically cannot rely that anything is there. So in worst case, you have to create everything from scratch for every request. And it's good to optimize it so that even in cases where you actually need to do the job, you do it before you need it. This is the same technique as CPUs nowadays use, which is called branch prediction. They optimize branches in the way that they compute both branches, if and else, and when you want to execute the code, and they know that one of the branches will be needed, you execute the if branch, the else branch is forgotten. But it's ready there because the CPU has the processing power while it's waiting for some other I/O operations. It tries to pre-compute so that it appears faster. So you can do this technique also to make your functions faster. Let me just quickly check the time because I don't have clock here. Okay. Another way to optimize runtime time, or spending the time you spend in execution stream functions, if you think about libraries that start fast, actually, and initiate connections fast, or basically don't have the burden that some applications, some libraries do if they want to optimize for long running. They optimize everything. They have all the options, and then they prepare in the beginning, and then they are ready for subsequent executions. Because in Lambda, you don't have so many subsequent executions, usually just one or just a few per each request. And then it's possible that your Lambda will be shut down and then recreated again. Then you basically lose this state, this prepared state, and you have to recreate it from scratch. So it's good in the cases where you really need it, when you really want to save some execution time and execution costs, you can choose clients and libraries that initialize fast. Then don't focus on preparing everything up front, but only preparing what they need to actually deliver one request. And for every request, it may be something different. So they postpone configuration or postpone creating the request until the very end. Or some libraries are even optimized to not run in Java. They use native code. For example, AWS AWS provides an HTTP client library that has Java bindings, but the actual implementation is in native code. So then it starts much faster and executes faster. So there's another way to consider if you really want to implement or optimize. Then one other hack, which is not so about optimization, but about deployment of functions, is that you can automate the infrastructure code also with Java. You can do it in different means. You can and outside of Java, there's CloudFormation. You can use AWS SAM, which I think uses XMLs, not XMLs, YAMLs. Um, and you can also use Terraform, which is a general tool that supports many cloud providers and many services. And I think it also uses something like YAML with some not so much uh, not so much flexible templates, but you can use something like define some variables and some methods, but it's not full-fledged as Java. With Java, you can really create objects and instantiate objects, and these objects would create, for example, your function environment, configure a function, your function with that amount of memory, create API gateway, connect them, create security groups, and things like that. And everything can be just one Java object if you create it in your code and instantiate it uh, during when you call the CDK. It will create everything. So in that case, you can have maintainable code that creates and represents your infrastructure. There is another option which is called Pulumi, which also has Java bindings. Both CDK and Pulumi support multiple languages, but I'm talking about Java. So if you want to use Java also for your infrastructure code, you can use either CDK or Pulumi. Here is an example of what I was talking about, how it looks like in CDK. One thing to note is this is actually Java code that is not executed against AWS environment. It's compiled to, or when it's executed, it creates a CloudFormation template, and that template is applied then to cloud. So you cannot run this from your application. You still need the CDK tool that runs this and creates the CloudFormation templates and then applies them. But it understands Java code. So it can run your Java code, and then this Java code creates the templates. And then your code can look like this. It will create a new function which has some name, defines a handler, which is actually a pointer to your application method that handles the incoming requests. And you can specify many other things like log retention to just keep logs for 1 day or more, memory size, as I said before. And you also specify the name of the deployment package, which is on your file system. So when you execute this code, it will find this function, this jar file, and add it to the deployment and deploy it with the CloudFormation template. If you create or somehow extend the function or create an object that has a method create or something like that, and calls this code, then you can have just one single method to call. You don't have to repeat everything like this, which is the benefit of using Java. You can encapsulate everything and then just reuse it. You can even create a library that can be reused and deploy it to a Maven repository and then just add it as a dependency into your projects. And all these works as a normal Java application. The only thing is that to actually apply it, you also need the CDK tool that runs your application, and the output of this application is the CloudFormation template. But everything works as Java. The CDK tool actually runs your application as Java, and produces the CloudFormation templates. So now about cold starts, and this is my last topic to address, which is very sensitive when we consider writing serverless applications. This is a general disadvantage of serverless functions. That's on one hand, you don't pay if your functions are not running, if your code is not running. So it can get very cheap to provision and maintain an application in production, at least if you don't have constant loads of incoming requests. If you have requests just, for example, at certain times of day or only in certain periods of year, and then you can scale up to thousands of instances and then scale down to zero then when you don't have any loads, then you can very easily save money. But the disadvantage is that when actually there is a new request and your functions are not running, or every time actually when you need to scale up and start a new instance to increase the number of running instances, you have cold start for every new instance. It can take several seconds, and then depends on whether this is visible or not. If it's visible to your users, then you might have a problem that the user will not wait for a couple of seconds to load an application and they will go away and not use your application. There are multiple things. I'll start with simple, easy to understand thing, which is optimization with the JVM argument. This start, stop at level. It's easy to apply, not so easy to understand actually what it does, but I'll try to explain in a few words. JVM, when it starts, it by default applies several optimizations. It compiles the bytecode that you have in your jar file or class files, processes the classes, processes the code, and also performs some optimizations already in the beginning. And it goes in two levels. One is it does very simple optimizations. The second level, it parses your code and tries to do some things like uh, turning your methods into inline methods and other bigger optimizations. But this optimize things from a long planning perspective, that you have an application that already can process incoming requests fast, but it takes time. If you disable these optimizations, you can save, from my experience, 10 to 20% of startup time just with these arguments. And then your function may take a little longer to finish. Maybe instead of half a second, 500 milliseconds, it will take 550 or 600 milliseconds. But you already saved maybe 200 or 300 milliseconds in the startup. And I don't know exact numbers. I think that the performance benefit of these optimizations is not so big as the benefit you get from reducing the startup time. The benefit you get only when your function is running for 10 minutes or 15 minutes. 15 minutes is I think the longest time your function can be running. Then it's killed by AWS Lambda service. So if you try to optimize for longer than 15 minutes, it's there's no point. Then another way to optimize cloud startup time is a mechanism that is not standard yet in every Java virtual machine, which is called, or in general, it's referred to as restore from a checkpoint. It has different names. And currently, I know of 3 different implementations, which are more or less the same in concepts. One is a project by Azul, a company with their Java virtual machines, which is called CRAC, Coordinated Restore and Checkpoint. which is a mechanism that basically allows you to hibernate a running Java application and then restore it from the exact same point it was before. It's like you hibernate your operating system, your laptop, and then you open it and it continues from where it was before, but meanwhile it was stopped. And here it also checkpoints the memory you have, the whole heap you have, all the open files, open connections, and there you might have a problem if you have connections open, but you can do this checkpointing before you actually do any work. So you can just checkpoint at a time when your framework starts, when your application starts, is ready to process incoming requests, but that only means that it's possible to call the method that handles the incoming object, or either event or HTTP request. And at that point, you don't have any resources open in general. And then you can restore it at the exact same point. Another implementation is very similar and is actually based on this crack. Is it's AWS Snap Start, which is very similar but implemented only in AWS Lambda by AWS, and it supports the same API. So actually, if you want to hook into this mechanism and somehow close connections before the checkpoint is created and recreate the connections when after the checkpoint is created, it supports the same API as OpenJDK crack, but it's implemented in a safer way, tailored specifically for AWS Lambda, and it's based on a special virtual machine operating system virtual machine which runs AWS Lambda environments, and is only supported in the built-in AWS Lambda environments. If you want to create your own runtime for running Java applications, you will have to use this OpenJDK crack mechanism yourself. But if you use already pre-built runtime, it supports Snap Start. And you just need to enable it, but it's not something that is very complicated. And then there is OpenJ9, which is a different JDK implementation, separate from OpenJDK, and it has its own CRIU mechanism, which I don't remember what it stands for, but it's very similar in this concept. It's good. It's good to, if you want to reduce cold starts with these mechanisms, it's good to also initialize everything before your method is executed. Especially in AWS Snap Start, it actually happens automatically before AWS handles your request, or after it finishes the initialization. Not even for an incoming request, but after you deploy, it starts and initialize your application, and then it stores the checkpoints. And then for newer requests, even if the application is not running, it restored from the checkpoint, and it saves time because it takes just a couple of milliseconds compared to normal cold starts, which may take even several seconds. So there may be great benefit if you have a framework that is not optimized for serverless deployments. With this AWS Snap Start or other mechanisms, you can really reduce it just to restoring the application just before it's ready to, or at the time it's ready to respond to requests. But to really benefit from it, you shouldn't initialize anything inside your method, because this method will be called only after everything is initialized, and it's called also for every request. So it's good to move every initialization into a static block or into a constructor, which is also called in the initialization phase. So this is an example how we would move things to static initialization. you create a static variable, initialize it in a static block. The same way would be if you created just my app field in the object and put these initialization in constructor. They are basically the same, because also the constructor is called before the actual method is called, and it's called during the initialization phase. So it's called only once per code for cold start, but once as soon as the application is running and warmed, this all is initialized. It doesn't matter if you have it in a static block or in a constructor. Another way to optimize startup time is to actually shift something from startup to build time. Uh, Traditionally, when we deploy applications to application servers or run them with some framework like Spring Boot, we have some configuration in our application which is not actually code, but some annotations or XML files or some configuration which has to be processed at startup. And it takes some time. Not much if you expect your application to be running for hours or days, but it may be significant if your application should be running for only for a couple of milliseconds or at most seconds, like for serverless functions. And then it makes sense to shift this to build time, so that at build time, you basically process this configuration and generate some optimized bytecode that already has this information and can be executed right away without scanning annotations, opening files and parsing JSON or YAML files. And another way is to optimize also the Java code. So this is another step uh, where you basically optimize what the JVM compiler does during runtime, and you do it before. And this is called compilation to native code, because for that you basically pre-compile everything before you run the application, which is like when you compile a C application, you compile it to a binary. And with Java, you can do that now with GraalVM project and GraalVM JDK. And with that, you can compile your Java code into a native code, which can be executed. And it's very fast to start, consumes even less memory than a normal Java process. And that's because it benefits from all the compiler optimizations done at build time. The disadvantage is that it takes much longer at build time than at runtime. Like when you try to run an application, a small application, unoptimized with native code compilation, it can start in a second, let's say. But when you try to compile it to native code with this GraalVM compiler, it can take a minute to compile, and then you can start it in a millisecond. So you see there is a trade-off, but compiling happens only once before you deploy to AWS Lambda, and then all the cold starts are instant. And for this, Quarkus framework is very useful. It's a framework that very nicely integrates both things, ahead of time compilation, and also if you choose it, you can easily compile to native code. It's very easy to use. It's pretty reliable. Well, I would say it is reliable. I'm using it on my projects, and I didn't see an issue with that. Um, and it requires just simple configuration switches to switch from normal Java execution to actually compiling to native code, and then you can run the binary. It requires some changes in how you deploy the application, because then you have to deploy it in a custom runtime. But this is also nicely supported by Quarkus framework, and it helps you with preparing all this. So I recommend using Quarkus if you build AWS Lambda functions, especially if you want to use the native code approach. If you want to use the Snap Star or this coordinated restore and checkpoint, then you can basically use any framework that works well with that, because you can also decrease the startup time to absolute minimum. It's just a little longer maybe a couple of milliseconds, while native native compilation is almost instanced. So there is a difference, but with it depends. In some cases, native code compilation does not, or your application may not need the requirement of native code compilation. It may use some library that is not compatible because there are some restrictions. Not many, but you may hit some restrictions. Some things work differently in a natively compiled binary than in a application running on JVM. So you may have some differences when you run native code in production compared to running your Java code in tests. So should be careful what you do with native binary, but in most cases it works very well. If it doesn't, then you have these snap start and coordinated restore and checkpoint mechanisms. Then you can use to achieve very similar thing and still run on a JVM that you're used to, and with the same benefits of running JVM. So I think I talked too much because I reached my time. So I'm sorry for that.
You never talk too much. That can't happen. You don't do it. I have one question here. It was asked earlier on in the presentation. So we might want to review the context. I'm not sure.
Excuse me?
Do you see the question?
No, I don't see the question. Can you read it out?
Yeah, I will. Let me just, okay, hold on. Let's do that. Any better? Still can't see it. It says, isn't caching an attached entity in a static homegrown cache a very bad idea?
Yeah, I received that question also before, and it's a bad idea in that sense that you can fill up the memory. So yeah, I didn't want to specifically go into details. I just wanted to explain the idea behind it. That in serverless functions you can use this approach, because the only thing running on that JVM is your code, and in most cases your code or the whole application will be removed at some point in the future. So you will clean up all the memory. But it may happen that you add too much into the cache, so you fill the whole all available memory. And in that case, it's good to have some more sophisticated caching mechanism which expires cache entries when you reach too much memory or after some time. Another approach is, which I haven't used, but I heard from Adam Bien that he uses a lot, is actually storing data into a file system, which in serverless, which AWS Lambda is almost as fast as storing things into memory. It's very fast. And if you just write things out into a file, you can also do this. It's similar approach because it's like a global thing for your application, but it's out of memory. So if you have issues that you run out of memory, you can store things into a file. It's still faster than going to over network to fetch the data from somewhere else. And it works the same way. You can only use it for caching because the whole environment can be removed at any time. But that's another option. I would first start with putting things in memory, implement some cache expiration if there's too much memory used by the caching mechanism. There are already libraries that do that. And if you want to store bigger things, you can store them in file system. I think it's several gigabytes to store by default.
Okay, all right. Well, Andro, thank you so much for this talk. A lot of great ideas in it, and we hope you'll be back next year to tell us. Oh, wait, whoops. Okay, another question just popped in here. Again, I'll flash it on the screen. It says, do you have experience with other FaaS providers besides AWS Lambda?
Not so much. I haven't used any other. I just know that Azure Functions, I think it's called as Azure Cloud Functions, from Microsoft Cloud, from Azure, they are also pretty nice because they have some things that AWS Lambda doesn't have that might be useful. One of them is ability to run multiple requests on a single instance of the function, which may not be so good because then you have to care about multiple things running in parallel. But you can actually benefit from paying only once for the CPU and processing multiple requests in parallel. And then you actually use what Java is good in, you use multiple threads. This is a little disadvantage of serverless functions because especially for Java, they are good for other languages which don't have good thread support, but Java has good thread support. So you can optimize performance by running many things in parallel in a very easy way with Java APIs. And in serverless, and especially in AWS Lambda, you can't really use that because you always just process one single request. So in Azure Cloud Functions, you can use it to some extent to process multiple requests in parallel and use the nice thread support in Java. But other than that, I don't have any real experience with other cloud providers.
Okay. Well, again, Andro, thank you so much for this talk. And those of you who are watching, join the next session. Go check out all the sessions, the remaining sessions today in the J Champions Conference. We'll see you again soon. Bye-bye.
Okay, thank you very much. Bye-bye.